First of all, I'm crying, but not for your question or answers. It's just this thing I have in the eyes. I don't know. So you will me see crying, but it's not for you. Okay. Hyperaccretion. Okay, so I've been given this title. And so I interpreted it. So for me, hyperaccretion is accretion above the Eddington accretion rate. Okay. So first of all, how many of you know what the Eddington luminosity is and know how to derive? Only the student. Only the student. I cannot count. 3, 4, 5, 6, 7, 8, 9, 10. Okay, good. So we're going to derive it because you are like substantial, but not the entirety of the class. And maybe we will learn something doing this. Okay, so we will do it together. Let's take plasma, a completely ionized plasma. And here are two particles of this plasma, an electron and a proton. In a plasma, you want to require charge neutrality, so no charge separation. And therefore, everywhere there is an electron, there should be a proton around. I'm thinking about hydrogen only. Anyway. And, okay, so let's consider this pair. So who is telling me, like in words, what is the Eddington limit? Hannah? Where is Hannah? Hey, you see, you were in front of me at lunch, and now I know you. Is the maximal luminosity that can be emitted by an accreting system, a spherical system. Okay, so now we are going to discover why is the maximum luminosity. And to do so, we are going to calculate first. So here there is the black hole or the accreting system. Okay. And radiation is diffusing outwards, and we see it, but a fraction is intercepting our system. A photon, for a photon, is the electron or the proton the biggest target? The electron. For scattering. You remember by which ratio?
Ratio of the mass.
Square, yeah. That's right. And since an electron is 2,000 times least massive, then you have this factor square bigger for scattering, for Thomson scattering. Okay, so the flux, as you know, in a spherical system, goes as the distance square. And now if I want the flux of momentum, what should I do? Divided by c, because the momentum of a photon is energy divided by c. And so I find the force per unit area. Okay. So now if I want not the force per unit area, but the force acting on the electron, what should I add, multiply by? This is the force per unit area, and I want the force acting on the electron, the cross-section. And then I want per unit mass. And so I divide by the mass of the proton. Why I'm dividing by the mass of the proton? I've been talking about the electron so far. Yeah, by what? Yeah. Coulomb interaction. So the mass of the system is dominated by the proton, but the cross-section for electromagnetic interaction is dominated by the electron. Okay, so the way I see it is that the electron gets a kick and then he carries the proton with it. Okay, so that's why I divide for the protons, and this is the Thomson opacity. And so we have this famous description of the radiation force, this known description of the radiation force. And this is what I said. Is there a typo? Ah, there is the C missing, okay. Sorry, the C missing. Okay, and then the other force is the force of gravity. As you see, it goes as R squared. And so when I equate them, there is no R dependence anymore. And we find this maximum luminosity that causes the mass of the accretor linearly. Okay, and this 10 to the 38 for 1 solar mass. Okay, so equality of radiation pressure on the completely ionized matter and of the gravitational force of attraction to the black hole. And this is from Shakur Sunayev. That's why it sounds a bit Russian. This is the description. Okay, so in this picture, there is something missing. Maybe it's not evident, but there is something that has been assumed, that I assumed, that we implicitly assumed. Spherical symmetry, that's right, which is we'll keep for now. And something else. It's like the system is an accretion system. It would be the same if it's a wind, but it's the mass is falling. Okay. Instead, I've kept my system fixed, and it's like I'm assuming that the time it takes for the photons to propagate from here to here is faster than the time it takes for the system to half its radius. In other words, I've been assuming that the fusion time for photons is much smaller than the dynamical time. Okay, so but let's, what if we take into account that these guys are actually going down when the luminosity is less than Eddington? Sorry. Of course, from the luminosity, then I come to that, but just this is from the luminosity, the Eddington luminosity, if we assume a radiation efficiency, we can derive the mass accretion rate, which I call M critical, because this kind of accretion I will talk about mainly is hypercritical. So it's not M Eddington, M critical, but it's the same meaning. And it's 3 × 10⁻⁸ solar mass per year for 1 solar mass black hole. Okay, but let's go back to our falling. Okay, so here there is a reminder for me. If I don't get to the end of the lesson, the whole point of the class is that the Eddington limit is a limiting luminosity, but is not a limiting accretion rate. And I'm going to show in the next slide so that if I don't get to the end, you got the message anyway. Okay. So now I'm taking a spherical accreting system, and my electron and proton are accreting, are moving. Okay. And I want to find a critical radius, which I call the trapping radius, where the diffusion timescale of photons actually equal the dynamical timescale. So in an optically thick medium, what I'm going to assume now, what is the diffusion timescale of photons? Or what is the velocity, the propagation velocity of photons? Do you remember? It's somewhat intuitive, but can be also derived. So in an optically thin medium, what is the velocity of propagation of photons? C. And now the medium is optically thick. Yes, what is rho kappa r? Tau. So this is the diffusion time scale. So basically, a photons goes slower because interact with matter. Okay, so it travels this distance with an average velocity which is smaller than c. And now I equate with the dynamical time scale, and I find that this trapping radius, the opacity, sorry, the optical depth is c over v. And then if I express tau like this, that, okay, it's okay if, for instance, rho is a power law. Then I can solve for R trapping, and I find this expression. So the trapping radius is very important radius in an accreting system, also in a wind, which is optically thick. So within this radius, radiation diffuses slower than the mass is accreting. Okay. Outside this radius, photons can diffuse outward faster than the mass can be accreted. Okay. So what is the consequence? Within the trapping radius, you can imagine that you are at the Eddington limit, for instance. In fact, the trapping radius, you can even be at the Eddington limit. And this radiation cannot stop the flow because the flow is going down faster. So the radiation is advected in the hole. So I can have accretion at a rate much higher than the Eddington because radiation is advected within the hole. So this was just an example to tell you why the critical accretion is not a limit. And okay, and then I will give you plenty of examples. And just to remind you, this is the accretion rate. So the flux of mass through an area 4 pi RT square. This is the critical accretion rate that we defined earlier, and this is the Schwarzschild radius. And this is, I believe, was defined by Mitch for the first time in 78 and 79. And I'll come back to this article because it's the first that makes this argument. Okay. Okay, but before telling you about hyperaccretion and talk about a different kind of disks, we're going just a step backward, and I want, like in 2 slides, remind you what is the classical geometrically thin, optically thick accretion disks. The one postulated by Shakur Sunayev, Lindenbell, and Pringle. in the early 70s. Okay, so are you familiar with the vertical and radial structure of this disk? Everybody, or you can say yes or no. Actually, who is familiar? Can you raise your hand? 1, 2, 3, 4, 5. Okay, so we'll go through it. Okay, so what do I mean by geometrically thin? Is that the height, the scale height of the disk, you can think about it as the density scale height or the pressure scale height, for instance, is much less than R at the given R. In the vertical direction, these are just then we will go in more detail. In the vertical direction, there is hydrostatic equilibrium. So there is no motion. The gravity is balanced by the gradient of pressure. In the azimuthal direction, particles rotate on a quasi-Keplerian orbit. For this disk, so-called, we will see that this is okay. And this is the orbital time. Okay. So the azimuthal velocity, so no velocity in the z direction, the azimuthal velocity is the Keplerian direction, the Keplerian velocity. And then there is another velocity, the radial velocity, because this flow is accreting. And so for, let's say, we put ourselves a little bit off the inner rim of the disk. The accretion velocity, the radial velocity, is just R divided by the viscous time. Because what we think is make the, so if you have a particle on a Keplerian orbit, this is stable. You can perturb it, it stays there. Okay? But now, in this flow, you have differential rotation. You have different part of the disk, adjacent part of the disk that moves at different velocities. Okay? And so if the medium is viscous, think in your head just for as an image, molecular viscosity. It's not what is acting in the disks, but to me it's the most intuitive. So if you have a differentially rotating medium and is viscous, what viscosity want to do? What does it want to do? There are two parts of the disk moving at different velocity. This, you want to equate the two velocities. You want to erase the difference in velocity. Okay? So for instance, the inner part goes faster. And so will be what viscosity would like to do is to accelerate this part and accelerate the other part. Okay. So this is called shear viscosity, and the net result, if you look at an annulus, for instance, you can see Pringle 1981. The net result, the net torque on an annulus is that you have a particle there. This particle is decelerated and wants to go and loses angular momentum and wants to go on a circular orbit on an inner radius. Okay. Okay, so that's why the radial velocity is determined by the viscous time scale. The viscous time scale, quite generally, is R squared divided by the kinematic viscosity. The kinematic viscosity is bears the imprint of the nature of the viscosity. So the kinematic viscosity is proportional by this factor alpha to the maximum velocity of the carrier. For instance, in this case, we want to redistribute angular momentum. So these are the carrier, if you want, of the angular momentum. And this is the maximum mean-free path. Cannot be larger than h, otherwise it's not collisional. You can think in this way if you have a molecular viscosity in mind. In disks, if you use the value for the molecular viscosity, you find out that you cannot reproduce these high luminosities that we observe. And so the luminosity is, since Shako and Sunayev has been proposed to be of magnetic origins. Okay, then the vertical structure. So this is the equation of hydrostatic equilibrium for the vertical structure. So the gradient in pressure, balanced gravity, the z component of gravity. And then if I use the fact that it's a thin disk, I obtain this simpler expression. And then I remember that the pressure is rho sound speed square. And then I say, okay, it's thin, so the pressure gradient is just P divided by H. And I obtain that H is the sound speed divided by, H over R is the sound speed divided by the Keplerian velocity. Okay. Let me see if I write it in, yeah.
Silly question. Don't you have to assume that you're adiabatic for B to be roughly Rossi squared and we are in a viscous system?
So what would you assume then? Why this doesn't work for you?
Because C.
What would you assume?
C squared is dp d rho at constant entropy.
Mm-hmm.
And this is a viscous disk, and so it's not adiabatic.
And so what would you use?
Well, I don't know, but I don't know if I would use that.
I think that I'm not sure about what you said. Yeah, exactly. Exactly. What I was saying is that what you are saying is that this gamma here, there is a prefactor here. It's a number.
Why is it? Sorry. Why is it? Wouldn't it be just the
P over
rho is the isothermal
yeah.
sound speed by definition.
Yeah, because gamma is equal 1.
Yes. Okay.
Because gamma is equal 1.
Okay.
Yeah. Okay. Okay. Okay, so H over R is C over V. And then we find that the medium here is highly supersonic. The Keplerian velocities in this disk is much higher than the sound speed. Okay. Another thing is that H over R is the sound speed divided by the azimuthal velocity. So if the medium is cold, so in a thin, geometrically thin disk, the medium, we say it's cold, which means the sound speed is less than the azimuthal velocity. When I will refer to a disk as hot, it means that the sound speed of the same order of the azimuthal velocity, and the aspect ratio H over R will be of the order of unity. And so a hot disk is thick, a cold disk is thin. And this is exactly what I mean when I say that. Okay, this was the vertical structure, and for the radial structure, you formally need to write the Euler equation. And then I just, take in the R scale and rewrite it like this with all the velocity we have been discussing so far. And so from our discussion, we know that VR is subsonic, is accreting very slowly, subsonically. So I can get rid of these two, and I find that the azimuthal velocity, as I anticipated, is basically in this disk Keplerian velocity with a correction due to pressure. This is the Mach number. When the disk is thick, then the sound speed is important, as I said. And so the azimuthal velocity they can slightly or somewhat deviate from the Keplerian velocity. Okay, and then the last things on the thin disk, because it's important, this is the accretion luminosity. You see that? So, as I think I mentioned last time, the accretion luminosity is the potential energy released per unit time by the mass that falls from infinity to r. So it's gm over r times the rate at which mass flows to r. And then there is this 1/2, because only half of the energy, of the potential energy, goes into heating. The other half remains in kinetic energy. And then if we assume that this medium radiates as black body, I see that T to the 4th is mm dot r to the 3rd power. And then if I look at the gravity force, I see again that they have the same scale. And this is important for the property of flow, of hyperaccreting flow. So now I'm taking all I've told you, and I'm going to high accretion rate towards the critical accretion rates. So the first property of flows that accretes close to the critical value is that h over r is roughly constant. And this is because what I just showed you is that if okay, I need to tell you the second property that I was going to tell you is that are radiation dominated. So in the vertical direction, if you equate the two, you find that h is constant. Okay. So the first property of a hyperaccreting disk that accrete close to the critical value, is that the aspect ratio is constant in R, and at 2r in of the disk, you can find that the aspect ratio is m dot over m cret. So as m dot get close to m cret, this aspect ratio gets to 1. Okay, so hyperaccreting disks are thick. Then hyperaccreting disks that are accreting close to the Eddington critical values, are radiation dominated. You can see this way. This is the hydrostatic equilibrium in the vertical direction, where P is P gas plus P rad, the radiation pressure. Then we remember that the radiation force is the momentum flux times per unit mass, is the momentum flux times kappa, the opacity. We derived that before. And so if I plug everything in, I obtain this, and then I solve for the luminosity, and I obtain that the luminosity of the disk is L Eddington 1 plus beta, where beta is P gas over P rad. You see that for a disk to emit at the Eddington limit, it means that beta is 0. So it means that it's radiation pressure dominated. So hyperaccreting disks are thick, are radiation pressure dominated. In general, Eddington flows, also like winds, radiation dominated, also winds, not only inflows, are radiation pressure dominated. Okay, and finally, hyperaccreting flows, winds or accretion flows, are hot. and in the sense I said before. And the main opacity is given by electron scattering. Okay. So this comes from Shakur Sunayev. And what Mitch calls the trapping radius, they were calling it the spherization radius. So, in Russian, yeah. And so for this light, in their honor, the trapping radius become RSP. But it's actually the same meaning. Okay. So what do we have? So in this paper, they explore what happens for the accretion when the accretion rate gets close to the critical value, and how the structure changes from the thin accretion disk I just explained so far. Okay. Yeah.
Going back, I have a question about the viscosity. So we assume that m dot, the accretion, is the same rate that viscosity we get in mass.
So accretion rate, the accretion is only given by the shear viscosity.
Okay.
Mm-hmm.
And therefore the heating from the viscosity is the same as gm m dot over r?
Yes, 1/2. Yeah.
Okay.
Exactly. Yeah. Okay, so, and is this. So the luminosity at the given R is G m black hole R times m dot. Okay, I forgot about 1/2. Doesn't. And then if I what do I do here? Yeah, sorry. If I use the definition of the spherization radius, I obtain the L at any R goes as 1 over R. Okay, so this means that the R greater than the spherization radius, so here L is below Eddington. This is Eddington. At R within the spherization radius, L is greater than L Eddington. So something must happen. And what they assumed is that, okay, the Eddington limit is a limit for accretion, even if this is not a spherical case, but you know, apart from a numerical factor, it's okay. So they cap the luminosity at Eddington for R less than the spherization radius, and if you do that, what do you need to need to impose? Sorry, to cap the luminosity at Eddington, what do you need to impose for the accretion rate within this region?
So it remains constant from the
if m dot remains constant, then the luminosity
so m dot over r.
m dot over R remain constant, and therefore m dot scale as. So the structure in this kind of hyperaccreting disk, m dot is constant here, where the disk emits sub-Eddington, and the luminosity is increasing. And then at this critical value, the luminosity wants to increase, but we keep it at Eddington. And to do so, we need to impose the m dot is actually decreasing with R. And so that less and less mass reach the black hole. Okay? Because it's a little bit what Rem told you about, you know, this is the highest energy that is is released is close to the hole. So you want the least mass possible to get the same luminosity. Okay, and so this is the famous inflow, I don't know, I'll call it inflow-outflow models, in which the wind transports away the energy in excess. Is transport a verb? Okay, good. To transport, yes. Yeah, you know. Okay, and then if I integrated the luminosity, so the luminosity is increasing here, then it's captured at Eddington. If I integrate over the whole disk, I get the famous result that the luminosity of this disk can be super Eddington, but just by a logarithmic factor. So if this is 10, for instance, this is a little bit more than 3. And so you can exceed Eddington in this in disk geometry, but by this factor only. Okay. Now that I told you like about the standard thin accretion disk, I can talk about structure of the disk as a function of m dot. So what I've been talking about so far is the geometrically thin, optically thick disk, and how it changes as we go towards m dot over m cret equal 1 and above, a little bit above, we will see. So generally, people think that this kind of geometry holds for accretion rates between 1% of the critical value and geometrically thin and 1. What happens below 10 to the minus 2? We have a radiative inefficient disk as opposed to radiative efficient ones, the one that I just described. So there are various incarnations of radiative inefficient disks. Let me just flash the classic ADIOS. No, ADAF. ADAF. Adduction dominating accretion flow. Yeah. So for instance, in this is a kind of flow that explains low luminosity AGN, or for instance, our galactic center. So in this disk, most of the mass, most of the energy remains, is carried by the protons into the hole. So the protons advect the energy into the hole. And in the classical ADAF version, the disk, which is hot and thick, because it cannot radiate, does not radiate because the time scale for transferring this energy to electrons is longer than the inflow time scale. So are the electrons the ones who radiates, but they don't get to get efficiently the energy because the medium is hot, thick, and tenuous. Okay, so in the kind of disk, most of the energy is advected in the classical ADAF version, is advected in the hole. And electrons and protons, for instance, at 2 different temperatures because they don't talk to each other efficiently. Okay, above 1 is the Hyperaccretion regime, which is the core of this class. And which is the least certain of the terrain. Okay, so what I'm going to do now is to talk about hyperaccretion. And what I did is to look at all possible models and make a classification and bunch them up in 3 classes. 2 have the sort of the same physics and 1 has a very different physics. And I'll give you a summary immediately. The idea is that the outcome depends on the relative position between the circularization radius and the trapping radius. At least, so these are the three categories I'm going to talk about. So between 1 and say 100 times the critical value, I will, so people think about hyperaccreting disk. When people think about hyperaccreting disk, think about the slim disk that I just presented. And in that case, the trapping radius is lower than the circularization radius, which is the radius of the disk. I will come back to this. So 100 is just a number that it depends on exactly on the condition of the plasma. But I took 100 because, for instance, 100 is the separation value for NTDs. Above 100, you don't have any more slim disk. You have a quasi-spherical flow. And in those disks, the trapping radius is actually larger than circularization radius. And then you go even higher, then the physics change, and you go back to a thin disk because it's no longer cooled by photons, it's cooled by neutrinos. And these are the disk that we think power gamma ray bursts. And so I'm going to talk about these three categories. Okay. Okay, so the first category is it's easy because I already explained. If we take some gas coming from a large scale with a certain specific angular momentum, remember that we did it for TDs, it circularizes to a radius which is dictated by its own angular momentum. This is the circularization radius we derived last time. Okay. If the specific angular momentum at trapping radius is smaller than the angular momentum of the infalling gas, then we are in this situation. And we have the inflow-outflow model just described, in which we have a thin disk outside the trapping radius, and that becomes thick inside. Okay. In which systems do we see it? In systems in which the infalling gas has large angular momentum, and or the accretion flow is not very highly critical. That's what I said, between 1 and 100 times the critical value. Okay. In this disk, the accretion rate through the innermost stable circular orbit is the critical radius, is the critical value. This is just a reminder. In this disk, we are not going above this. And the black hole increases exponentially with a time scale of 0.5 gigayear. Okay, in which astrophysical environment people has argued those disks explain what we see? In X-ray binaries with hyperaccreting mass transfer, in ultraluminous X-ray sources when there is a neutron star as accretor, and in microquasar outburst. And then we have this thin, thick geometry. And this is for solar mass black hole. And for supermass black hole, in TDs, when they are mildly Eddington, both TDs and these sources show observational evidence of winds. That's why people think that they lose most of the mass by winds before getting to the before the mass reaches the hole. Okay, and let me talk a little bit about TDs in this regime. Okay, so the trapping radius is 100 Schwarzschild radii for a black hole of 10 to the 6, and I take this efficiency. The circularization radius we saw last time for TDs is twice the tidal radius, which is around 100, Schwarzschild radii. And so if I ask for which mass of the black hole the circularization radius is equal to the trapping radius, the answer is 10 to the 6. So this is a critical mass. Let's see. Okay, so this is my PowerPoint diagram. Okay, let's see if you see it. This is mass of the black hole in unit of 10 to the 6. This is radius. This is the trapping radius. The trapping radius decreases with mass. Was on the previous slide. The tidal radius increases with mass, 1/3. So there is what we just calculated, the mass at which they are equal. And this is this mass here. Okay, but then there are the other critical radii. There is the Hill's mass that we talked about last time, remember? So this is the trapping radius. No, sorry, this is the trapping radius. This is the Schwarzschild radius. Here, the Schwarzschild radius is larger than the trapping radius, and then what happens? We saw last time, when the Schwarzschild radius is larger than the trapping radius. The Schwarzschild radius is larger than the trapping radius. What happens to the TD, to the star that is falling? This is the tidal radius. This is the trapping radius. This is the plunges. We don't have TDs here, so we don't have disk. And so I take this out. Okay, but then there is another critical radius here, which I call the Eddington mass. And what is the Eddington mass? This is the famous fallback for TDs, remember? And this is the peak return mass, which is for 10 to the 6, 100 times the critical value. Sorry, this is m dot cre. And if I ask for which mass of the black hole this ratio is 1, I obtain 10 to the 7. Okay, so let's go back to this. So above this mass, TDs are not hyperaccreting because even the peak return rate is below Eddington. Below this mass, we are in the hyperaccreting regime. So between here and here, we are in the hyperaccreting regime, and the trapping radius is smaller than the circularization radius. So between 10 to the 6 and 10 to the 7, we are in the slim disk regime. Below that, the trapping radius is larger than RT, and I will explain what happens. So this is the Hill's mass. This is the Eddington mass. So I decided to call this mass for this talk M. Rossi. So there. I didn't know how to call it, so I gave my name. Okay. I thought it was funny. So Tal Alexander told me that he was working on, he was in Princeton working on a paper on stellar dynamics in galactic nuclei, and he was using the result from the Bacall-Wolf paper. And then he gave the paper to Bacall to read. And gave comments, and one of the comments that Bacall gave to him was to name the r to the minus 9, what is it? 7/4 as the Bacol-Wolf cusp. So since Thal's paper, we call that a slope the Bacol-Wolf cusp. So if Bacol can, I can. So this is the M. Rossi. This is M. Rossi for this talk. And so that's why between 10 to the 6 and 10 to the 7, we may use, if the circularization is efficient, the slim disk model that peaks in the soft X-rays and gives the t to the minus 5/3 in soft X-rays. And then we know that there is the mystery of the optical. And this and TD is show-ins, as Nadia's work nicely shows. Okay. And now we go to the other. And now we go to the other category. Now we take a flow that has a specific angular momentum such that it circularizes within its trapping radius, so that we have the opposite. Okay, so it circularizes within the trapping radius. So in these circumstances are the most uncertain. And really, there is a zoo of possibilities, and so I will give a qualitative picture. There isn't any coherent, well-defined, mathematically well-defined, coherent scenario for all sources. Okay, so. In this condition, the gas falls and deposits its energy and angular momentum well within the trapping radius. So in a very opaque region, and I remind you that the trapping radius is the radius within which the flow accretes faster than the photons can escape. Okay. In this case, because of what just said and the argument, Michi's argument that we gave initially, in this case, you can exceed arbitrarily m dot crit. In the slim disk, no. Here, yes. You can have highly hyperaccreting. There is no formal limit. In which sources people has argued we have this kind of flows. In TDs, I just showed you, below 10 to the 6 for black holes, less massive than 10 to the 6, but also in the high redshift universe, hyperaccreting AGNs, and the model for growth of supermassive black hole seeds. Okay, so I explained the TDs, why we can have the condition that the trapping radius is larger than the circularization radius. Let me tell you why in high redshift. When I mean high redshift, I'm really thinking about even before the reionization. What are the conditions for hyperaccretion there? And then, and then we come like close to home. For small, have you heard about cold flows? Cold flows? Yes, no? No. Okay. So at high redshift, and for small halos, smaller than 10 to the 11 solar masses, roughly. What simulation shows is that halos are fed by from the cosmic web by cold filament of baryonic matter with very low angular momentum that penetrates the virial radius of the halo, and they call this cold flows. So this is in opposition to what we were thinking before, like a Rees and White picture, in which the gas would instead shocks, get hot, and then slowly settle in. This is, it's called hot accretion mode, and we think happens for higher black hole masses, halo masses, and a low redshift. Okay, but if we take the cold flows, this is the accretion rate through the virial radius. So a redshift 15 for a halo mass of 10 to the 9, so a proto-galaxy. You can have a few solar mass per year, okay? And let's imagine that you are creating these proto-galaxies, and at the same time, a small black hole sits in the center, and you can funnel somehow all this material down to the potential well. Then you have that this accretion rate corresponds to 10 to the 3 times the critical value for a black hole of 10 to the 5, or 100 times the critical value for a black hole mass of 10 to the 6. So for a small IGN, you can have, you are in the hyperaccreting regime. And of course, if you have a black hole, supermassive black hole seed, maybe 100 solar masses, then the factor is 10 to the 5. Also, if we go at even higher redshift, maybe redshift 20, when we think the first stars were formed, the first population of stars, with masses up, I'm taking the upper limits, 100,000 solar masses, in a halo of 10 to the 6, 10 to the 7. Then you have in cold flow inflows, which is extremely high. And again, you have mass inflow rate, which are 10 to the 3, 10 to the 4 times the critical. So people recognized that, and thought, okay, we can grow black holes at high redshift supercritically, perhaps. Do you know why there is the need to, make them grow fast? Supermassive black holes at which redshift?
At least redshift beyond 6.
Yes,
Observe.
that's right. So we observe extremely massive black holes up to the 10 solar masses, redshift 7. And the question is that there is so little time to grow those masses, and so how is it is possible? So one option is that you form big black holes in first place. Another option is that you form them small, but you make them accrete super Eddington, or at least you have episodes of super Eddington hyperaccretion. Okay. And the arguments come from the cold flows. Okay. So what I showed with these two slides is that the higher redshift, in principle, there is enough gas for hypercritical accretion. Then whether the circularization radius is within the trapping radius then depends on the specific system you're looking at. Okay, so historical paper, 1979. So here, formally, the circularization radius is 0. So this is the first paper that look at hyperaccreting. The first paper that argued that radiation pressure from a spherical accreting black hole cannot prevent the accretion rate from attaining arbitrarily high values, which is just what I told you. So what Mitch takes here is a spherical accreting black hole. So it's a Bondi flow, spherical accreting black hole, but is hyperaccreting, so it's radiation pressure dominated. And what you find is that as the gas falls in, part of the potential energy is converted into internal energy, which is mostly in radiation. Most of the energy is advected in the hole, and the fraction leaks out. At infinity, we can see an Eddington luminosity. All the rest is dragged into the hole. Okay, so this is the picture, the first picture that I mentioned to you. And here there is no circularization, so certainly the circularization radius is much smaller than the trapping radius. And that's why you get this result. A version of this...
Elena, you have a question. Maybe it's too shy to ask.
Okay, Sylvan. Sylvan,
So,
I hope I can...
So I'm just trying to see if I can understand this picture symmetry. So if the trapping radius, if the circularization radius is inside the trapping radius, the photons still feel an outward force larger than the gravity, but the velocity is too high, so the force can't decelerate them before they fall to the black hole.
No.
This is how you...
Okay, so here there is no emission from the black hole, okay? The flow is falling into the black hole and affecting the energy with it. And the version of this, in which the accreting black hole instead moving, but otherwise it's the same picture, is the one proposed by Tal Alexander and Priya Natarajan, to have POP3 seeds accreting at a super-exponential rate. So what is the picture? So this is the large cold flow rates I mentioned before, 10 to the minus 2, 10 to the minus 3 solar mass per year. Here there is a 10 to the 7, so it's a very small halo, 10 to the 7 solar masses halo, a redshift 20. There's been the first generation of stars. One of the stars was massive and gave birth to a black hole, but like 10 solar masses. So this is not much more massive. So this is not difficult to imagine the possibility to have a 10 solar mass black hole here. And they are in equipartition. And the black hole is scattered by the stars, and it wanders around. And while doing so, is accreting matter through its Boyndy-Hoyle-Littleton radius or capture radius. So they work out which are the conditions for this to happen, that the circularization does not happen outside this radius. They work out which are the conditions for the gas not to circularize, but to fall directly into the black hole. And it turns out that that gives a limit to the mass of the black hole. When the black hole becomes much more massive than the star, it sits in the middle of the potential well, and then the gas circularizes outside, and you cannot have anymore this hyperaccreting mode of growth. And if you take that accretion rate, then you have, as I said, the super exponential growth. So the mass diverges at a finite time. Okay, and so this is a version of Mich's radial flow with a moving target. Okay, shouldn't be there. Okay, so these were two examples in which there was no circularization radius. So for sure, we were in the regime in which the circularization radius is much smaller than the trapping radius. Okay, and now I give you the last, few slides, very short slides. Instead, example in which the circularization radius is not zero, and so there is accretion energy to the presence of a viscously accreting disk just outside the black hole, and this energy is given back to the flow, to the infalling flow. Okay, so there is an extra ingredient here to energy, accretion energy liberated close to the black hole. Okay. There is something missing here. This part. Okay, so what happens? What people imagine that happen when there is release of accretion energy in these highly trapped flows. What people think is that the energy, the accretion energy that is injected into the flow, inflate the flow until it finds a sort of hydrostatic equilibrium. So it's, it creates an envelope which is mainly pressure supported, so it rotates slowly. It completely radiation pressure dominated, so from the virial theorem we know that it means that it's very weakly bound and it's quasi spherical, and at the edge of the envelope it emits Eddington, and he has an accretion disk inside. Okay. So where does it happen? Where it has been proposed to happen? In tidal disruption events. And I work out which are the conditions for this to happen. So for masses less than 10 to the 6, the mass, the Rossi mass. And what Eric Kaufling and Mitch envisage is that the extra energy is funneled in a jet. Okay, and you have just Eddington instead emitted by the envelope. This is the case in which the envelope surrounding the black hole is much less massive than the black hole, so the envelope is not self-gravitating. Then Mitch also and Marta Volonteri applied the same models, which is called Zebra. 0 Bernoulli something. Anyway, the Bernoulli constant is 0 here. In high redshift AGN, so they work out that here the circularization radius is less than the trapping radius, and you can have, in those cases, hyperaccretion. And then there is another physical object in which this has been envisaged. But in this case, the mass of the black hole is much less than the mass of the envelope. And self-gravity becomes important. Okay, so there is no theoretical picture, coherent theoretical picture that goes from here to here. So this is a piece of theoretical work that is missing if someone wants to work on it. And so let's go to this object, which I've been working on. Okay. So if you think about making black hole seeds in a proto-galaxy, while the galaxy itself is forming, people have thought a lot about it. And you have these cold flows reaching the in some condition, this cold flow can reach, or a substantial fraction of them can reach the center. And what people, I think, the consensus is that if this amount of gas reaches the center without fragmentation, then what's born is a massive star. So there are hydrogen burning in it. It's very short-lived because it's massive, so 1 million years. And then the core collapses into the black hole, and the rest of the envelope fall onto it. If the envelope, and we work out the condition for this to happen, circularize outside the small black hole that is formed by the core, then you have the kind of hyperaccretion we are talking about. So the black hole starts accreting, inject energy. You have an inflated envelope, which is in quasi-hydrostatic equilibrium. So it's called quasi-star because it's like a star, but the energy here is not given by nuclear energy, but accretion energy. Okay. And how this energy is transported? It's transported by convection. And you can transport by convection a flux which is higher than the Eddington flux. The Eddington flux is the limit when radiation is transported by a radiative transfer, not by convection. Then you have 10 to the 6 solar masses. So here, for instance, like it's 10 to the 6, and this is maybe 100 solar masses. So the energy is transported convectively in this radiation-dominated environment. It may work, may not work. But this is the picture. And then it gets to the radiative layer, where suddenly the convective flux reaches its maximum. And now radiation has to be transported radiatively. And matter realized that is, this flux is super Eddington, what do I do? And so the idea is that you form photon bubbles. So the atmosphere is porous, and radiation escapes through holes. This is it's been worked out in some analytical, and there are some also simulations that seems to support this, the presence of this porous type of atmospheres in super Eddington objects. But at some moment, this is not enough, and the super Eddington flux hits the matter, then needs to and push it away because it's super Eddington. So here, the radiative force wins over gravity, and there are super radiation pressure dominated super Eddington winds. Okay. So the extra energy is gone with the wind. You can also have a jet, but the picture is that you have like very, very strong winds, mass loss. Okay. So how much time you have?
A few minutes.
Okay. So this is the final. I have 3 slides. Okay. And now we are going even higher. And this was meant actually to then reconcile. So I tried to touch the disruption events, and now gamma ray burst. So the topics that you have been hearing about, some of the topics you have been hearing about in this school. So let's go even higher rates. When 2 neutron stars merge, or in a core collapse supernovae, you can have accretion rates onto newly formed compact objects that can be greater than 0.01 solar mass per second, not per year, per second. So for instance, you take the collapse time of 10 seconds in a collapser and 1 solar mass collapsing into it, you can get this accretion rate. These are enormous. This is 10 to the 13th time the critical accretion rate we have been talking about. So these disks turns out to be fundamentally different from what I've been discussing so far. In fact, these disks have extreme conditions. The density is very high, and the temperature in the innermost part is greater than 1 MeV. And this means that there is neutrino production. In fact, these disks are cooled by neutrino emission. The photons are trapped and advected into the hole. Now, this is the critical accretion rate we have been talking about so far. This is the corresponding critical values, but for neutrinos. So in here, there is the neutrino cross-section rather than the Thomson cross-section. And you find out that this critical values is 10 to the 19 times higher. Okay, so this is higher than this. And so these disks are sub-Eddington for neutrinos emission. So neutrinos can cool very efficiently, and we go back to the thin accretion disk, alla Sakura-Sunayev. Okay, so again, in the inner part, there is neutrino productions, photons are trapped, electrons are mildly degenerate, and this was a note for me, which I didn't do it. Okay. And it's neutron rich. The fact that it's mildly degenerate is why it is neutron rich. Okay. I told to myself I needed to write the beta decay next time. And this is the radial structure. It's fascinating, so we just go through it. And this is basically the last slide. So outside this radius here, the flow is made mainly of alpha particles. And here, there is no neutrino cooling, and so it's a very, very thick disk, and there is wind. Then, the matter passes this radius, and the temperature is high enough for the alpha particle to dissolve, and from here on, we have free nucleons. Here is the radius at which the temperature becomes greater than 1 MeV, and there is neutrino emission, and the disk becomes thin. If you go on, the disk may become mildly opaque for neutrinos and antineutrinos, but we are really talking about tau of a few. And here is for certain very high accretion rate, neutrinos are trapped. Okay. And the last slides is like a jump in the past. This was like a paper that I did in 2005. And in fact, the slides is also from 2005. So it turns out that if you calculate the time for the matter to be entrained and escape in a jet, this is shorter than the beta decay time, the time for a neutrons to go back to a protons by beta decay. This means, as also showed by these authors, that the jets produced by this, accompanying this accretion flows should be neutron rich. The fraction of neutron of protons is larger than 1. And also in the jet, as it expands, there is very little nucleosynthesis. So it's really a neutron-loaded jet, which makes gamma ray burst jets spatial. And this is the last things I wanted to say. Thank you.